Okay, so this is homework 8, problem 2. And so we're given that the joint density function is a times the absolute value of x plus y and 0 otherwise, where x is greater than 0 and less than the absolute value of y, which is less than 1. And that graph looks like that. The bounds will look like that graph over here. And so in the first part, we are asked to find a, to make a such that the joint density function is valid. And so we know, so in this case, we're going to do the dx dy first. And so we know the bounds of x are bounded from 0 to y, and then since y is the absolute value of y, there also exists negative y to 0. And so our integrals become the integral of negative 1 to 1, of 0 to y, of a x plus y. So since x plus y, and that takes into account the positive values of x plus y, and since this is the absolute value of x plus y, we also have to do negative a of x plus y, with the bounds from negative y to 0 instead of from 0 to y, since y is now negative. And so integrating that out, we get a times negative 1 to 1 of x squared over 2 plus yx, which is the integral of the above, from 0 to y, plus a times negative 1 to 1 of negative x squared minus negative yx from negative y to 0. And so that simplifies to a times negative 1 to 1 of 3y squared over 2 dy, plus a times negative 1 to 1 of negative y squared over 2 dy. And so those two just add up to simply y squared. So it just becomes a of negative 1 to 1 of y squared dy, which is equal to a of x cubed over 3 from negative 1 to 1, which is a times 2/3, and all that has to equal 1 because the integral of the density function is equal to 1, and therefore a is equal to 3/2. In the second part, we are given that z is equal to x times y, and we want to find and draw the density function of z. And so there's two components here. Since the bounds are 0 is less than x is less than absolute value of y is less than 1, z could be positive or negative. Since y can be negative, and therefore y times x, which is always positive, so therefore z could also be negative. So we have to split this up into two components, where z is positive and where z is negative. Both will have different equations. And so there's a variety of ways to approach a problem like this. One way is to simply just to draw the bounds of the area of z. And so since z is equal to x times y, then y is equal to z over x, and you can see that graph. You can see that graph here. And you know it's bounded by 1 to 0 for x and 1 to 0. I mean 0 to 1 for x and 0 to 1 for y. Because y is going to be strictly positive in this case, because z is going to be strictly positive in this case, then our y is also going to be strictly positive in this case. So we only take into account the first quadrant. And so since we're only interested in this shaded region here, because it's just the intersection of, as you can see, the bounds up here, this bound up here, and the graph of y is equal to z over x. So we're only interested in this shaded region here. However, it's probably easier for us in this case to find the area of this entire region and simply just divide it by 2, since these two areas are equal. And so we'll equal in this case because our equation is symmetric. And so big F of z is equal to the integral of 0 to z and 0 to 1 dx dy of our equation here, which in this case is 3 over 2 x plus y. So that's the first part. And that takes account into this rectangular chunk here from 0 to z and 0 to 1. So now we have to do this other chunk here, and this integral takes account of that, plus z plus 1, z to 1, and 0 to z over y of 3 over 2 x plus y dx dy. And so this becomes 3 over 2, 0 to z of x squared over 2 plus yx from 0 to 1 plus 3 over 2 of z to 1 of x squared over 2 plus yx from 0 to z over y. And that simplifies to 3 over 2 of 0 over to z of 1 half plus y dy plus 3 halves 0 z to 1 z over 2 divided by 2 y squared plus z dy. And so that simplifies further. When you do the integral of this integral, you get 1 half y plus y squared over 2 from 0 to z. And if you do this integral, you get negative z squared divided by 2y plus zy from z to 1. And so after you do out this integral, you end up with big F of z is equal to negative 3 halves z squared plus 3z. But we also find small f of z. So we simply just take the derivative of that, and the derivative of that becomes negative 3z plus 3. Okay, so this is f of z for this entire area. But since we're only interested in 1 half of this area, we divide this equation again by 2, and that becomes our small f of z. So 3 halves 1 minus z for when z is greater than 0. So that is one way to get f of z for when z is positive. An alternative is that there already exists an equation, a formula for the product of two random variables, and that is small f of z is equal to the integral of negative infinity to infinity of 1 divided by the absolute value of y times f of z over y, comma y. So we replace every x with z over y, and we replace every y with y dy. And so when we plug that in, we get from the bounds of y, which go from 0 to 1. So 1 divided by, 0 to 1, sorry, for all positive values, for only positive values of y, which is the one we're interested in here. Because positive y's give us positive z's, which is what we're interested in. And so when we plug that in, we get the 3 hasn't come out in front. So it's 0 to 1 of z plus y, z divided by y plus y divided by y, because this y here. And so that gives us the integral of 3 halves times 0 to 1 of z divided by y squared plus 1 dy. And so as you can see, when you integrate this out, you end up with what we have before, 3 halves 1 over z. And now we have to evaluate z for when z is negative. And we can do that by using the Jacobian method. And so we know that z is equal to x, y, and therefore w will just be equal to y. Let's say w is equal to y in our case. And so since we know that x is equal to z over y, and y is equal to w, then x is equal to z over w. And therefore to find the Jacobian, we take z dx, and then z dy, and then w dx, w dy. So that gives us yx 0, 1. And multiplying this matrix across, we get this equal to y. But since y is equal to w, we just set that Jacobian to equal to w, because we want to integrate with respect to w. So we want to put everything in terms of w. And so I have an example here for the bounds you would have used had this been only positive. The bounds would be from z divided by w is less than w is less than 1. And so we multiply everything by w, and we get z is less than w squared is less than w. But we know that w is going to be equal to 1 because the upper bound is equal to 1. And so when you take the square root of everything, you get square root of z is less than w is less than 1. So when we do the negative z's, it becomes a little more complicated. It's essentially just the flip of this equation. So we flip this equation, or we flip this inequality, and we get negative 1 is less than or equal to w is less than or equal to negative z divided by w. When you multiply w across by all sides, you get negative w is less than w squared is less than negative z. And then w, is bounded by at least negative 1. So it's negative 1 is less than w, is less than, so you would take normally the square root of negative z, but that would result in a positive value. We want z negative, so we added negative in front. Okay. And so we use this formula for when you use the Jacobian. So f of z is equal to just f of xy of z divided by w, comma, w, all divided by the absolute value of w, which is our Jacobian here. And so the bounds of w are from negative 1 to negative square root of negative z times, we put our function here, so it would be 3 over 2 times the 1 over w here, times the function of x plus y, x replaced by z over w, and w replaced by, y replaced by w. And so when we do the integral, and we integrate it out, we see that our answer becomes 3 halves of negative 2 square root of negative z minus z plus 1. And so this is our small f of z for when z is negative. And so that becomes our f of z, 3/2 to 1 minus z for when z is greater than 0, and what we got before for when z is less than 0. And so we can quickly check that this is a valid density function by taking the integral over its bounds. And so we integrate the positive values over the bounds from 0 to 1, because it can be at most 1, and similarly the negative bounds from -1 to 0. And we get that, when you integrate it out, you can do it yourself, but you get 0.75 plus 0.25, which is equal to 1 at the end. And so what f of z looks like is from -1 to 0, it looks like this graph here, which is not linear, and it has area under it of 0.25. And then from 0 to 1, it is linear. So with height when equal to 0 of 3/2, and it goes all the way to 0 when at 1. And so that is problem 2.